So I guess, do you just want to give a brief explanation of what your goals were, what you set out to build, and then maybe demo what you've got and talk through how you put it together?
Mm-hmm. So you'll see the hardware in a minute once I get this camera up, but we wanted to acquire data through software-defined radio, send that data to an FPGA to be processed so it could be visualized in some form of frequency domain representation, as well as identify the modulation scheme that was being used on the signal we're trying to capture. So in that case, if you wanted to tune to an FM radio station and have it automatically detect that by using a convolutional neural network to predict that that's FM versus AM versus a different modulation scheme such as like QAM or BPSK, which all have different frequency spectra and time domain shapes, which allow the CNN to try to differentiate between the two, between them. This is pretty important. This can be pretty important with software-defined radios nowadays, since they might want to try to just capture a wide range of signals and decode them. And if there's no person manually looking at these signals, telling it what's what, it has to figure it out. And then it can try to decode those signals. This could be used for like cyber security or surveillance.
Gotcha. So just to make sure I understand properly, you had the software-defined radio is gathering raw I and Q RF samples, presumably hooked up to the HPS. And then those raw samples are being communicated over to the FPGA. There's a neural net implemented on the FPGA that's taking in the raw data and figuring out what the modulation scheme was for that data and doing some visualization as well.
Yes.
Okay.
Yeah, and you can see the software, or a radio transmitter next to an antenna, and then the small rectangle hooked up to via USB is the software-defined radio receiver that we're using.
Gotcha. One of those little RTL SDR dongles.
Yeah, but I'll put this back in for the better visualization. Okay, so I can start screen. If I want to show the screen sharing, it's disabled at the moment.
Here, let me enable it. Should be good now.
Okay. So this is our system, or a display. I'm gonna start up let's make sure that the process to capture the IQ samples and send them over TCP isn't running. Of course it is. It's relatively tricky to actually kill it in the HPS program. But when we start our for this program, we have it classifying between AM single sideband, wideband FM, and Gaussian frequency shift keying. And I'm going to tune the radio. It asks me for a tuning range, which we wrote, and a sample rate and kilosamples per second. And then I'm going to use max gain to maximize our chances. And then I will start up the MATLAB script, which goes between these three different modulation schemes. And
the MATLAB script is toggling the transmitter.
Yes. Yeah, so it'll cycle through single sideband AM, FM. So let's see if it wants. Okay, so have all the pieces in place, but that is actually GFSK based on the spectrum we're getting in the imagery. You can see the lines there. And then it's actually, I think, going to FM right now. So that's what, so you can see it trying to guess, and it's not sure whether it's GFSK or FM, which is a side effect of just a relatively small neural net. And then it's going to go back to AM, which it predicts pretty well. And occasionally.
So at the top, we're looking at a real-time visualization of the raw data. And we can visually see in that data what the modulation that's being used. And then down at the bottom, we're seeing what the neural net thinks the modulation is.
Yeah.
Very cool.
Is that the Hadamard transform we're looking at there?
Yeah. So that's the fast wash Hadamard transform. We used it rather than an FFT, as it only required approx 100, or it only uses real additions and subtractions, which are easy to implement and don't use as many resources as if we wanted to implement it with multiplies. We couldn't do 128 point transform in 7 cycles. So if we used an FFT, we'd have, maybe we could use like 10 multipliers or so, maybe 20, depending on how many we had, and then try to sequentially run one iteration and then have to repeat that process like half a dozen times to get through the 128, and then do that 7 times. So that would take a few hundred cycles instead.
How did your intuition work on Hadamard transform? Was it understandable in a fairly quick way?
In terms of the visualization, or just how the transform works?
Well, no, in terms of the visualization, in terms of data understanding.
At first, we were very unsure because we were trying to pick up local FM radio. We just got it working. So if you put the transmitter pretty close, it gets better signal noise ratio, and it shows up in the transform properly.
So presumably you am I correct that you would have trained this neural net offline, right? And then implemented it. So how did you do the neural net training?
Yeah, so Peter can.
I can share my screen and kind of talk through like the process of that.
Okay.
So basically, we use TensorFlow to kind of train our model offline, and you can kind of see the layers that we have. So first, we take in our data and we want to reshape it in the way that it's a 2 by 128. So we have 128 samples, and the 2 stands for the I and the Q data. And then we wanted to pad it so that when it goes through the different filters, the ones on the ends don't lose any features. And then finally, we go through the convolutional layer, which has, our final one has 3 kernels. We started off with 10 kernels, but once we moved on to the FPGA, we realized that was just way too many parameters to try to fit on there. So we reduced it to 3 filters, and the filter size is a 1x2 filter. So it's kind of basically going through each IQ for each sample, and it will give us a value based on how the kernel, does multiplies by element wise. And then what happens then is the model flattens it. And this was kind of tricky because it was kind of hard to understand how TensorFlow was flattening the model in terms of like, was it IQ, or was it just a bunch of I's for the first 129 samples and then Q's? And so that was kind of like a difficult challenge, but we were able to figure out how exactly it flattens it. And then finally, after that, it goes to the dense layer, which essentially is, we have 3 different classes. So here you see wideband FM, AM single sideband, GFSK. And for each of those 3 classes, we have a set of parameters that is going to be then multiplied to this flattened array. And so in the TensorFlow, they actually have an activation at the final step for softmax, which essentially shrinks all these big numbers into a value between 0 and 1 to give like a proper prediction. But we didn't really feel the need to do that because on the FPGA, we just needed to look at which value was the highest or which summation was the highest from the dense part. And so essentially after we train it, like you're saying, Hunter, we did have to do a lot of this offline. So then what we would do is we would have these, so we had a bunch of different, we wanted to try a bunch of different classifications. And here the GFSK one is the one we kind of stuck with, but essentially we would train the model, get the weights, try to read these weights offline, and then go through a bunch of formatting using Python to get it in the format that we wanted. So for the convolution layer, we formatted it in the way that you had the I weight, the Q weight, and then the bias, and then I weight, Q weight, bias for the different samples. And then we would essentially just kind of do similar things. The dense weight was the place where we had the most weights. I think it was around like 2,325 weights. And we essentially had, we had to format it in a ROM table because we didn't really, we thought, the other options were maybe reading through the SD-RAM or kind of creating a state machine to read through the different data. But we realized with the ROM table, it would only take like a single cycle to determine what exactly the weights were. So we had 6 different ROM tables for essentially the first table was the I data for the first class, or the I weights. And then the second table would be the Q weights for the first class. And then it would just repeat for the other 2 classes. And so then this information then was, sent over, put on the drive as a text file, and then Yunyun can kind of go over a little bit about how the actual Verilog works, but that was sort of how we trained the model and then tried to replicate it over on the FPGA. So if, yeah, and in terms of, once we were able to get the weights, a lot of writing the code for the Verilog was reading some research papers and kind of understanding what these matrix multiplications were doing. But I think Yunyun can kind of go over
I
that.
can like show the Verilog code about it. Yeah, here is kind of the code we here. So we have first one will be the convolution computation one. So for each one, we will be do the computation on the weight 1 times the first I sample, then plus the weight 2 times second I sample, then plus the bias will be produce the first neural for the convolution layer. Then we just like keep repeating it with 129 times. And we do the IQ at the same time for the parallelization. And we also do the samples in series. Then we do the kernels also in the parallel manner for the computation. Then we fitted the output from the convolution layer to the dense layer. Then for the dense layer, we do the parallelization for the for 3 classes, and at the same time for the I and Q weights. So we use 6 DSP to do the parallelization to compute the dense layer. Then we play with the sign extension manually because the Verilog has some troubles to do that automatically. So we also fit the data and extend the for the multiplication, we use the 6.12 format for the all the multiplication, and since it will be densely, it will be increment and add all the neural produced from the convolution layer. So we extend the output data from the 18 bits to 22 bits, just avoiding the overflow issue. Then the final one will be output as 3 predictions on 3 classes. And this one will be do the ReLU activation functions. If it's negative, we just like filter out as 0. And if it's positive, we just leave it. So that's the implementation of the CNN.
And then what happens is we'll have like 3 final values for the predictions that's sent over to the HPS, and then Parker decides which values are biggest and then outputs the class. So, yeah.
And the actual process that we get the IQ samples is a little, it has to go through a few steps. So so we have that neural net running in the background, but we are every time new data appears or is sent by the SDR over TCP to the program that's running on the HPS, we collect those data. We actually have to offset it by 128 because it's mapped from 0 to 255, and we want to actually have positive and negative values as they are actually. So we do that on the HPS, and then we have to they come in as interleave samples, so they're coming in IQ. So we toggle between those and write those to the appropriate location on SRAM on the FPGA. So that's actually, I think, M10K blocks in the end. And then we have a state machine on the FPGA, which sees that the data has all been written to the SRAM and starts reading from that SRAM and then feeding it into a register that can be used for both the Walsh-Hadamard transform as well as the neural net. So the transform runs in parallel with the whole neural net, and the convolution layer runs in so the dense layer runs in serial with after the convolution layer. At the moment, we wait for the convolution to be finished. Theoretically, we could we could also pipeline this, so we could try sending more data, but we didn't deem it necessary for the 1 megahertz bandwidth we were working with.
Okay. And when you send back the 3, I guess on the HPS side, when you're making a decision about which modulation you think it is no modulation an example, or does it always pick one?
It always predicts one. Actually, surprisingly, when you look at most neural nets, they don't have like a no case. There's not usually a no case. There should be probably an other, but it's pretty tricky to add that because what is white noise? It's noise.
Sure.
That's actually a pretty interesting topic, probably on its own, right? How do you tell a neural net to say no? It doesn't know what it is.
Sure.
But
and I noticed too. Sorry, what'd you say, Bruce?
So this is sort of this is supervised learning, right?
Mm-hmm.
Yeah.
You have to label it something, but what would you label it if you didn't?
I noticed too, in playing with those software-defined radios myself, I know that they have a big, they'll buffer if you're not keeping up with them. And on the command line, it lets you know that you're buffering outputs because you're not keeping up. It seems like you're keeping up. I didn't see a buffer accumulating.
We only saw so the buffer accumulates at the start if you're not fast enough to type things in, because it'll start trying to grab data from a preset,
right?
Like a default. But once you set it, it clears it pretty quickly, assuming you're under, I think, 1.5 megasample per second. And it manages to keep up. If you go around, I think the max of the SDR over USB is 2.4 megasample per second, and that starts to overflow after a few seconds, I think. But
at the sample rates that you guys are using, it keeps up just fine. So there's no.
yeah, we haven't noticed anything. The only thing you can notice is just like occasionally there's a glitch on the screen from which you actually can see in person, probably from Linux doing some scheduling tasks. So it,
Okay.
because it's actually context switching between the loop that's checking if you're waiting, if you want to input, change the for like gain or the sample rate or the frequency, because we can do that dynamically, and it just sends it across the FPGA, and it also just has to collect those samples and forward them, which is, well, has to run. It basically uses 99 to 100% of the CPU. So
Sure.
I think this actually has 2 cores, so we could potentially play with scheduling on that. But
And you're so in the demo that you just did, you were sending those transmissions from a separate radio there inside the lab. So the signal to noise ratio is quite good. Were you able to pick up and classify any radio waves just out in the world? Like I think the air traffic control uses AM, I think, right? Were you able to pick up anything like that?
I was able, so we weren't able to get really anything too distinct when at least visualizing and trying to classify with this system. When I attached the SDR just to a computer that can show a FFT of the frequency spectrum, I saw I couldn't find air traffic control, surprisingly. FM radio, depending on the station, was reasonably strong, but you had to play with the gain settings to get stuff to behave. And I assume just our system likes really high SNR that's probably saturating the input. And that seemed to work best. That we had to get in testing, we had to get the antennas pretty close to each other to actually pick up stuff. I assume if you end up using a much higher end SDR that didn't have an 8-bit ADC, maybe something higher like 10 or 12 bits, and had some better filtering, you'd probably be able to get some better results without even having to change the neural net. But an alternative to that would just be to use a bigger FPGA that could hold a bigger, more complicated neural net model.
Sure. That's very impressive. This is a very infrastructure heavy project. There's a lot of stuff that had to talk to each other, and the amount of things that you guys got to talk to each other is very impressive. Yeah.
Also, one of the few neural nets I've seen that actually did something on the FPGA. It's impressive. So how much of the neural nets use a lot of resource? How much of the resource did you end up using?
Well, at some point, we dropped from 10 kernels to 5 kernels. And since that actually reduces the dense layer as well, because it's outputting less data from the convolution, it made a pretty significant decrease. So I think we were originally at 50% utilization with improperly used ROM tables, and that was logic limited because of the ROM tables. The fast Walsh Hadamard transform, depending on how accurate you want it to be and whether you want to use like amplitude or phase data, can add some computation, so that takes up a good chunk. But the neural net, I think, once in the end with 3 kernels and then the full dense layer of like 2,300 parameters, was, I think it used like a third to a half of the AL logic on it. We could have pushed it harder, but we were having compilation issues, and you'd absolutely be able to fit a bigger one if you move all the weights off into SDRAM or request them from the HBS. But we could add it, basically the second you add another layer, either convolution or dense, it basically is very infeasible on this. I know if you have a bigger FPGA and you want to actually implement a neural net of any sort, you probably are the best options to not hard code it like this and use a high level synthesis language, which might take longer to compile, but lets you tweak some parameters a little more readily.
Yeah, like the research papers that we were kind of like reading in the beginning had like 50 kernels, like 6 or 7 layers on their FPGA, and like when we started like implementing it, we're like, there's no way, like it's just not going to be. And so then, and that's why we also had to reduce it down to like 3 classifications.
There are some FPGAs though that are gigantic. They're used for this kind of research.
Yeah, I
Some of
think
them
they
have,
cost 10 to 20 grand.
yeah, they have thousands of multipliers
Oh.
and millions of ALMs.
You guys got something to work though. I mean, that,
Yeah.
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 Very
Yeah.
impressive.
I think that in the end, I think the trickiest that it was making sure that the neural net was all the steps were going in the right order and there was no like incorrect indices. And then the last issue I think was just the order of the weights. It wasn't even the implementation, it was the integration with between other software. So if you're dealing with a black box, good luck.
Yeah.
There's like barely any documentation out there about like how TensorFlow is flattening their arrays and like how to really interpret their weights. And so we really just had to like play around and just until like things started clicking.
Yeah,
So
and we
the-
do a lot of testing of that.
Sure.
Like our
Is it-
drive, yeah, it's filled with like
It's-
20 different test samples.
Because that software is meant to be internally
Yeah.
consistent, but not necessarily externally.
Yeah.
Yeah.
Yeah, and if you reorder your own model, you end up actually having a different order of the weights. And
Yeah.
I think our first few weeks were figure out how neural nets behave and what we're doing wrong, because we realized that we had way too many parameters to start with. Then we cut down some parameters, and then slowly but surely we were getting different features to behave.
But now we really know how neural nets work. So
Yeah.
Yeah. That's a good outcome.
yeah.
Lori says the snow is here, and so it is.
Just starting here.
Oh
Yeah.
my, we're in for a long night full of snow.
It's supposed to
It's
snow
gonna
a
be
lot.
what are you looking at? 8 inches in Ithaca, I think.
Yep,
Yeah.
yep. Anyway, I don't have any other questions. I think this has been really successful and a really impressive job.
Thank you.
Very, very interesting. Very nice.
I was gonna include this in my like course overview, but I just want to say now, I think this class has been my favorite class at Cornell. And this is my last semester, and it's just been one of those classes where like the things I'm learning, I'm seeing right away how it's being applied, and that's just been so cool. And some of my other classes at Cornell are very like theoretical, and so like I just took so much away from this class. So just wanted to thank you guys, and even though it was remote learning, I learned a lot. So I really enjoyed it.
Makes me really happy to hear that. Yeah,
That's good to hear.
yeah.
Thank you.